When we look up at the night sky, we are looking through a dense, three-dimensional volume of space. For astronomers parsing the initial Data Preview 1 from the Rubin Observatory, the objective is to isolate a specific group of stars, the globular cluster 47 Tucanae. The challenge is that a telescope captures a flat, two-dimensional projection. We see our target cluster, but it's physically sandwiched between foreground stars in our own Milky Way and background objects deep in space. Right behind 47 Tucanae sits the Small Magellanic Cloud, a dwarf galaxy packed with its own dense stellar population. This image shows the resulting optical collision. The foreground Milky Way stars, the 47 Tucanae cluster members, and the distant Small Magellanic Cloud all collapse into a single crowded plane. Visual inspection alone cannot separate them. Because static X and Y coordinates contain multiple overlapping populations, we have to look for a different sorting metric. We have to look at how these stars move. That metric is proper motion in right ascension, denoted as mu alpha star. This measures a star's horizontal movement across the celestial sphere over time, calculated in milli-arcseconds per year. Because the Milky Way field stars, the 47 Tuc cluster, and the Small Magellanic Cloud occupy different regions of space and hold different galactic orbits, they travel at distinct speeds and trajectories. We can effectively separate these three groups using only the single horizontal dimension of movement. The mathematical tool that allows us to filter these populations is a one-dimensional Gaussian mixture model, an unsupervised machine learning algorithm. Proving that a single parameter model works demonstrates that we can build highly accurate initial data filters without the computational overhead of multi-dimensional tracking. To test this sorting pipeline before applying it to raw telescope data, we build a simulation in a Python Jupyter notebook. First, we plot Milky Way contaminants as a wide orange distribution centered near 0.0. Next, 47 Tucanae stars form a sharply peaked blue curve centered at 5.5. Finally, the Small Magellanic Cloud is a green curve centered at 1.0. If we were looking at perfect categorized data, our job would be done. But a telescope does not output neatly labeled, color-coded distributions. It records everything at once. In our simulation, we concatenate these distinct arrays into a single, unordered list of movement values. This gray histogram is what raw observational data actually looks like. The identities are stripped away, leaving an overlapping, non-normal distribution. The goal of our pipeline is to take this opaque histogram and mathematically reverse engineer the distinct populations hidden inside it. For that reverse engineering, we rely on the Gaussian mixture module from the scikit-learn Python library. Before the algorithm processes any data, we have to define a single crucial parameter, the number of components. We set the n components parameter to exactly 3. This is where astrophysics informs data science. We know from observing the visual field that we are looking at 3 distinct spatial structures. If we specified 2 components, the algorithm would merge distinct groups. If we set it to 4, it would arbitrarily split a real group. Aside from knowing there are 3 groups, the model is completely blind. It starts with no knowledge of velocities or relative sizes. The human operator provides the structural constraint of 3 populations. The unsupervised algorithm handles the precise mathematical mapping. We execute the command gmm.fit. The algorithm analyzes the raw input array, evaluating only the one-dimensional proper motion values. Under the hood, it uses an expectation maximization process. It generates 3 invisible statistical curves, iteratively shifting their centers and adjusting their widths until they optimally match the raw data. Once locked in, we extract the calculated centers. The algorithm successfully outputs mean values near 0.0, 1.0, and 5.5, identifying the correct velocity peaks without prior prompting. Next, we extract covariances for standard deviations. The model accurately determines the 5.5 peak is tightly bound, while the 0.0 peak is chaotic. Finally, it extracts the weights, giving us the relative percentage of total stars belonging to each distinct group. This table displays the final parameters recovered directly from the raw dataset by the mixture model. By pulling these specific arrays, we convert a visual mass of overlapping stars into 3 strictly defined statistical profiles. We can map these extracted parameters back into individual probability density functions to verify the algorithm's accuracy. Over the raw histogram, we plot the reconstructed curves, the wide-orange Milky Way baseline, the green Magellanic Cloud, and the sharp blue 47 Tucanae spike. Tracing their sum creates a total fit perfectly aligned with the raw boundary. The one-dimensional model successfully slices through overlapping datasets that simple, hard-coded velocity cutoffs would fail to separate. Defining the three populations is only the first step. The ultimate objective is to look at a single star and confidently determine which group it belongs to. We do this using the algorithm's predict.proba function, which analyzes a star's specific velocity value on the x-axis. By measuring the relative heights of the overlapping curves at a precise coordinate, the model outputs a fractional likelihood. For example, a star moving at this exact speed has an 85% probability of being a cluster member and a 15% chance of being a Milky Way contaminant. Astronomers use these percentages to create a strict boundary, discarding any star from the final catalog that fails to meet a high confidence threshold for the 47 Tucanae cluster. Assigning these probabilistic tags turns a chaotic raw observation field into a cleaned catalog, ready for specific astrophysical analysis. This Gaussian mixture model operates as a critical intermediary step. It sits between broad initial brightness cuts and highly specific color-color diagram filters. While our model relied strictly on proper motion and right ascension, stellar movement is two-dimensional. Stars also move vertically, across declination. We can use the declination data as an independent check. If the model correctly sorted the stars using horizontal movement, their vertical movement profiles should also cleanly separate into distinct distributions. Running the data through a two-dimensional algorithm would yield an even sharper separation, but at the cost of significantly higher computational overhead and pipeline complexity. The fact that we can achieve robust separation with just one variable proves the efficiency of mixture modeling for unsupervised learning. As the Rubin Observatory scales up to process exponentially larger datasets, lightweight, mathematically elegant filters like this will be essential to accurately mapping the sky.